I would like to talk about the Modulo today, which is a model-based testing tool. It's specially designed for finding convergence failure bugs in distributed systems with Divergence Resync Models. These days, there are various cloud services and large-scale web applications relying on distributed systems. In this talk, we'll focus on replicated distributed storage systems, where each replica is a key value store, trying to keep its data set in sync with other replicas. Here's one example convergence failure bug we found from Jira bug database of ZooKeeper. So its priority is labeled as blocker, which means it's one of the most severe bugs. And its reproduction step is as follows. So you start server 0 first, and then create some data items on the server 0, and you shut down the server 0. Then you restart server 0. This time you also start server 1, and these two servers are supposed to be replicas. But then clients cannot read those data items on server 0, while clients can still read those data items on server 0. Clients cannot read those data items on server 1, but can read data items on server 0. So servers are out of sync. Clients may read inconsistent data and make incorrect decisions based on that, which may result in catastrophic events. So Patrick Hunt, who is the author of the ZooKeeper paper, left a comment saying, this is a serious issue as it's causing the follower, which is the server 1, to get an inconsistent view of the database. So it's a serious bug. And here's another example bug we found from the same bug database. And this bug requires a long sequence of events to be interleaved to find it. So these types of bugs can be pretty difficult to find. And also this bug resulted in several subtasks. A couple of them are still not closed, and bug itself hasn't been resolved, and it has been 10 years. And we found there are other similar bugs in the bug database. So it's a recurring problem. So we need some kind of automated bug finding tool for these types of bugs. So what happens internally is as follows. So let's say there are two clients, and client 1 sends a put request writing value 1 for some key. And after some time passed, another client expects to read the value that's written by the previous put, which is 1 in this case. And the key enabler for this is convergence property that keeps the replicas consistent. What happens is client 1 sends put request, one of the replicas commit that operation, it becomes different from other replicas, so replicas diverge, but then replication protocol works, and other replicas replicate that operation, commit it, so their data set becomes equivalent, so replicas converge. Then client read data from arbitrary replica and still get the consistent value, which is value 1. But what if a replica fail after commit the write operation? So in this case, if replica that committed the writing for the key with a value 1 fail, and it becomes unavailable for replication. Therefore, unless the failure is recovered, divergence across replicas remains. Once failure recovery is made, resync mechanisms run, and replicas replicate and commit the operation just like the other one, and they become converged again. So that's how they reach convergence. But if there is a software bug lurking in the resync mechanisms, it may manifest in certain divergence resync scenario, and some of the replicas may suffer from convergence failure. In this case, the convergence may never occur again. And we call these types of bugs convergence failure bugs, or CFBs. And if a client happens to read data from these faulty replicas, then it will read the inconsistent data. So there are existing approaches to find bugs in distributed systems. Model-based testing and model checking use state space exploration. They systematically and exhaustively explore the state space of the system under test. But their state space exploration is usually generic and not targeted. Therefore, they may easily suffer from the notorious state explosion problem. On the other hand, manual testing and random testing explore state space randomly, but their state space exploration is neither exhaustive nor systematic. So they make miss corner cases. Our approach is targeted, systematic, and exhaustive state space exploration. And because it's targeted, we mitigate the state explosion problem. And because we systematically and exhaustively explore the state space, we don't miss the corner cases. We made one key observation that we can convert the sequence of complex events, such as the one on the left-hand side here, into a much shorter sequence that's concise and reproducible, just like the one on the right-hand side, involving the relevance events such as crash, put, restart, and resync, for example. And we can interleave these to find new CFBs. We further can reduce these steps into divergence and convergence. So by focusing on exploring various interleavings of divergence and convergence can reduce the state space explorer significantly more. And also we separate abstraction from the concrete execution. We developed the Divergence Resync model for that. This Divergence Resync model, or DRM, represents various divergence resync scenarios. It is composed of abstract execution model, or AEM, and concrete execution model, or CEM. AEM models the target abstract behavior, and CEM models the target concrete behavior that's compatible with the abstract behavior modeled by AEM. So AEM is essentially a finite state machine. We use the depth-first search strategy, and state exploration is actually a repetitions of past exploration. Each past exploration starts at the initial state and traverses down each state that hasn't been visited previously, and it ends at the leaf state where there is no more next state to visit. And we repeat this until we visit every state in the state space. So we exhaustively and systematically explore the state space of AEM, then produce schedules. Each schedule is basically path we just explored. So it's a sequence of divergence and convergence. With this, Modulo generates the inputs and injects it into the system under test to find the bugs in the real distributed systems. And benefits of separating abstraction from concrete execution is twofold in Modulo. So first, AEM can be reused for different systems under test. And the common functionality of the CEMs that's repeatedly implemented can be compiled as a library. Modulo's architecture is pretty simple. It has two components, schedule generator and concrete executor. User must specify and provide a DRM, including AEM and CEM. AEM is going to be given to the schedule generator. CEM is given to the concrete executor. And CEM is essentially a system under test wrapped by a control layer. So schedule generator is the one that explores the AEM's state space and produces schedule files containing a bunch of schedules. Concrete executor takes each schedule and executes it by generating input based on it and injecting those inputs into the system under test via CEM. After executing each schedule, Modulo performs a bunch of read operations to see the values of each key on every replica and check if there is any key contains the value that's inconsistent across the replicas. If inconsistent keys detected, then Modulo raise an alarm for detection of convergence failure bugs. Now let me explain more detail about how Modulo use DRMs. So I'll use an example DRM we used for ZooKeeper. In this example DRM, we have two state variables for the AEM. And those are replica state and online state. User must specify the number of write operations to inject as normal PS and the number of replicas to use as num replicas. With the num replicas given, we can determine the size of arrays for state variables. And each index in the array is for each replica. So first index is for replica A, second index is for replica B, and so on. And then with the num OPS given, we can generate the predefined write sequence. We write values that are monotonically increasing. And based on this, we can index each write operation to distinguish it explicitly. So replica state represents up to which write has been committed by replicas so far. And online state represents the availability of each replica. So here's one example state S0. It's actually an initial state. And in this state, every replica has committed the first write operation. So set data is the write operation we use for ZooKeeper. And so their key access values are all 0. So state variable for S0 should be set as follows. So replica state should be set as 0, 0, 0. And online state should be set as true, 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 which means every replica is converged at the very first write operation, and they're all online. And each state has a bunch of enabled transitions. And let's say we pick the divergence transition, which represents a divergence scenario where we crash the replica B first and then inject a write operation. So replica A and C committed, then A and C crash. If we apply this divergence transition to the S0, we get to the next state S1, where replica state is set to 1, 0, 1, which means A and C has committed the second write operation, but B did not because of the failure. And online state is set to false, false, false to indicate every replica is crashed. In S1, there are also a bunch of enabled transitions. And let's say we pick one of the convergence transition, which represents the scenario where we restart A and B and then let them resync. If we apply this transition T2 to S1, we get to the next state, S2, where replica state is set to 1, 1, 1, which means replica B successfully replicates the second write operation, and all the replicas actually converge it. And online state indicates that A and B are online while C remains crashed. So with this, we can perform path exploration, and path exploration produces a schedule, which is a sequence of divergence and convergence transitions. And concrete executor takes each schedule and get its transition and translates it into the more concrete test inputs. So for example, for divergence transition, it translates it into the intermediate representation where crash B and write 1 to X and crash A and C are executed, which is actually get further translated into more concrete test inputs, which is kill -9 for B, set data, thread.sleep, kill -9 for A and C. And similarly, for convergence transition, we can translate it into restart A and B and wait for resync, which will get further translated into Java to restart the A and B and scanning the logs for certain messages to be printed out for the indication of the resync. And once inputs are generated, concrete executor injects them into the system under test at the correct timing relative to some internal events. So for example, we have a thread asleep for divergence transition after set data, but before kill -9 for A and C. This is to ensure that A and C commit the injected write operation before they get crashed. So if we don't have this time delay, it's possible that A and C crash before they commit it. So the test is going to be deviated from our intention. And for convergence, we have scanning the log after restarting the A and B. This means we wait until the leader election completes and resync completes. Otherwise, it's possible in the next transition, write injection is made, but fail because there is no leader elected yet. So we need these kinds of non-determinism control. Modulo is implemented in 8.k lines of code in total. Schedule generator and concrete executor are only 0.3k lines of code and 0.8k lines of code, respectively. Divergence Resync Models takes up most of the code, which is 7.3k lines of code. This includes all 5 DRMs we implemented. And among these, AMs are 2.8k lines of code and CMs are 4.6k lines of code. And we applied Modulo to ZooKeeper, MongoDB, and Redis. As a result, we found 11 CFBs, and we newly discovered 5 CFBs in ZooKeeper and 1 CFB in MongoDB, and we reported them. And we also detected 1 known CFB in MongoDB and 4 known CFBs in Redis. And we found that the size of state space to explore is small enough so we could finish the systematic and exhaustive state space exploration for the AEM of DRMs we use to find aforementioned bugs. Also, we could reuse AEM for both ZooKeeper and MongoDB, so it shows that Modulo is supportable. And we made the repeated portion of CEMs for Redis's DRMs as a library and implemented each Redis's DRM by extending based on the library. So it also shows that Modulo is extensible. So in conclusion, Modulo is effective in finding bugs in real-world distributed systems. Our key approach is targeted, systematic, and exhaustive state space exploration. And key ideas are exploring only interleaving of divergence and convergence, which mitigate the state explosion problem, and separating abstraction from concrete execution via AEM and CEM. Therefore, Modulo becomes more portable and extensible. And so Modulo can be extended to find bugs in your distributed systems. And the code is here in the GitHub. So thank you very much, and I'll take any question now.